A civilization that harvests a star's energy rewrites its own destiny. The Age of Dyson Spheres imagines megastructures that encase suns and turn their light into power, life, and exploration. This opening view breaks down what a Dyson sphere could look like, why it would change technology and culture, and how we might detect signs of such civilizations across the galaxy. You'll see the engineering challenges, the energy economies, and the philosophical questions that emerge when a star becomes a shared resource. If humanity ever climbs into this era, our world, our politics, and our sense of possibility would look nothing like today. Stick around to explore the bridge between imagination and physics, and why the search for Dyson spheres reshapes how we think about intelligence in the universe. Origins of Dyson spheres. Freeman Dyson proposed that a civilization capable of harvesting most of its star's energy would surround the star with a vast network of energy collectors in orbit. The core idea, first laid out in a paper in 1960, was to scale energy capture beyond planetary resources. In his formulation, this system would gradually accumulate power by placing innumerable satellites or structures in carefully arranged orbits, creating a living solar economy around a single sun. The term Dyson sphere comes from this broader proposal, though the early emphasis in the original work is on a swarm of devices rather than a solid shell. A solid shell around a star would face serious stability problems. A swarm of independent collectors avoids that pitfall and forms the basis for most theoretical discussions. The origins are tied to the idea that a truly advanced civilization would need energy far beyond what a planet can supply. This pushed thinkers to imagine enormous, engineered structures around a star. The original argument favored a distributed array of solar collectors, which could be built progressively as resources permit. That distinction between a shell and a swarm remains central in both academic discussions and science fiction. The concept also influenced SETI thinking, where infrared signatures or unusual energy budgets might hint at megastructures. The scholarly origin contrasts with popular imagination, which often shows a single, perfect sphere around the sun. In practice, however, a distributed swarm is far more plausible. Contemporary work models orbital dynamics, material science, and deployment strategies for swarms, rings, or modular habitats. Early ideas thus seeded a field that continues to explore if civilizations can scale energy capture to extraordinary levels. The origin story remains a hinge point between engineering fantasy and astrophysical plausibility. Stellar energy as a civilization resource. Stellar energy is the most abundant usable resource for advanced civilizations. A Dyson-inspired architecture treats a star as a central power source rather than a distant furnace. By capturing nearly all of a star's output, a civilization could power vast computation, industrial processes, and planetary-scale construction. This shifts energy from a constraint to a background enabler, altering economics, technology, and daily life. The concept exists in variants: a swarm of habitats that collect energy, a shell that encloses the star, or a hybrid network. In practice, turning stellar energy into usable form involves multiple stages. Collectors, mirrors, lattices, or panels convert light into heat or electricity. A grid translates that energy into forms: high-density power for industry, low-grade heat for climate control across habitats, and specialty outputs for computation. Storage is essential to cope with variability and maintenance cycles. Beaming energy across long distances is possible with directed radiation, enabling remote colonies and mobile units. Maintenance requires autonomous robots, sensor networks, and fault-tolerant architectures. Risks include structural failure, debris, and fluctuations in the star's activity that ripple through the power system. Economically, energy becomes raw material, currency, and strategic leverage. Civilizations may trade energy credits, invest in research to improve capture efficiency, or dedicate energy to social services. A highly centralized energy regime could accelerate large-scale projects, while distributed swarms offer resilience and local autonomy. The design choices influence social organization and governance. The management of such a resource also shapes incentives, priorities, and long-term planning for future generations of technology and infrastructure. Looking ahead, The feasible management of stellar energy depends on reliability, redundancy, and interoperability. Diagnostics and repair networks maintain the health of collectors. Redundancy minimizes outages. Beaming methods offer flexible power to fleets and colonies without large infrastructure on the ground. It also introduces potential security concerns and the need for secure control of energy flows. Observationally, such civilizations would appear as unusual infrared or optical signatures. The search for technosignatures often considers energy management scales. In practice, the abundance of stellar energy could redefine growth trajectories, requiring policy frameworks that balance ambition with resilience and environmental stability. Megastructure architectures. A Dyson sphere is a megastructure concept designed to capture a star's energy output and channel it to a civilization, spanning architectures from dozens of autonomous collectors to a rigid shell. The idea traces back to Freeman Dyson and has become a staple in discussions of megascale engineering. In this family of architectures, the energy source is the star, and the enclosing structure acts as a large energy farm. The practical challenge is immense. Architects imagine networks that scale from mounting thousands of tiny satellites to entire planet-sized habitats. The most credible near-term architectural solution is a Dyson swarm, a tapestry of mutually independent solar collectors distributed across many orbital positions. Modules function as power harvest units. Each node sits in a controlled orbit, harvesting energy and emitting it via microwaves or lasers toward a central receiver on a planet, an orbital habitat, or a fleet. Redundancy is built in. This modularity supports incremental construction, easier repair, and resilience against orbital debris, and it scales with technological and resource budgets. A Dyson bubble variant uses large sunshades or sails arranged in a loose lattice that shades portions of the star while transmitting light and heat. The structure need not be rigid, and control systems keep the collective surface oriented to maintain a desired insolation. Shades can be deployed to tailor planetary climates, support agriculture elsewhere, or direct energy where it is needed. Stability is achieved by dynamic balancing. Material challenges are less severe than a full shell, but still daunting. A hypothetical Dyson shell compresses a star's power into a single, continuous shell, a configuration that is often used in fiction but faces severe physics limits. Realistically, no known material can withstand the star's tidal and radiation forces at 1 AU. Even if such a shell could be built, its own gravity would pull it into destabilizing modes unless constantly corrected. That active stabilization demands energy, propulsion systems, and huge mass. Scientists typically treat the shell as a thought experiment illustrating why swarms or bubbles are far more plausible. Constructing any of these architectures relies on in-situ resource utilization and autonomous robotics to mine, process, and assemble materials in orbit. Robotic factories would weave solar collectors from asteroid-derived materials. Energy beaming, via microwaves or lasers, would deliver power where it is needed, enabling propulsion, desalination, or city-scale power without ground infrastructure. Safety and ethics come into play with beam weapons and environmental risk. Astronomers search for infrared excess around stars as potential signs of megastructures. Missions like WISE have provided the precedent for such observations. Societal evolution under stellar power. Enclosed by a thriving network of habitats, factories, and computational cores fed by the captured stellar output, a civilization broadens its reach without exhausting planetary resources. Energy abundance reshapes everyday life. Labor shifts from physical toil to design, curation, and software governance, with maintenance and construction handled by autonomous systems that operate across orbital rings, lattices, and microgravity facilities. People plan cities around light and heat rather than rivers and ore. Economic logic dissolves scarcity constraints, giving rise to provisioning networks that can allocate power, food, and materials instantly to regions in need or to experiments in remote habitats. Markets become resilient coordination layers. Education emphasizes complex systems thinking, astroecology, and ethics of sentient agents, while apprentices learn to tune energy flows as a social craft. Culture adapts to scale. Governance evolves into polycentric and technocratic models where distributed AI councils, citizen juries in orbital habitats, and consortia across chambers of a Dyson structure negotiate priorities. Consent can be algorithmically mediated. Religious and philosophical impulses transform, with new rituals around the life cycles of stars and the stewardship of vast energy reservoirs. Identity often centers on stewardship rather than conquest. Communities mentor younger generations through mentorship networks. Risks include cascading failures if energy management frameworks fail, political rifts when different regions demand priority, or rogue intelligences misaligning with human values, all of which pushes resilience engineering to the fore. Redundancy and layered security help. Interstellar diplomacy becomes a discipline of trust-building with neighboring civilizations or subsystems, trading energy credits for knowledge, and sharing climate control know-how across worlds connected by the energy grid. The arc favors enduring adaptation over spectacular feats. Engineering feasibility and longevity. A Dyson sphere is a theoretical megastructure designed to harvest a star's energy by surrounding it with an array of collectors that capture radiant power and funnel it into usable forms. The engineering challenge is not only scale, but reliability. Different architectural options exist, with a swarm of independent collectors preferred over a solid shell because it dissipates risk and accommodates incremental construction. A full shell remains the most demanding concept. Feasibility hinges on material sources, autonomous manufacturing, and in-space assembly using robotic fleets that can mine, process, and assemble components without cosmological supervision. Power transfer across the system must be wireless or modular. Longevity demands that modules operate for eras with minimal human intervention, so redundancy, standardization, and self-healing capabilities become design defaults. Modules fail. Redundancy means many parallel collectors and power paths, so a failure in one unit does not collapse overall output. Diagnostics run autonomously. Protective shielding against micrometeoroid strikes, radiation, and dust, plus materials that resist thermal fatigue and erosion, extend life and reduce maintenance frequency. Materials will need to be rugged and reparable. Self-healing coatings, modular replacement parts, and robotic repair crews can reconstitute damaged sections, while phased aging credits keep the overall system balanced as components degrade. A practical path couples phased deployment with standardized modules that can be created in situ, shipped to orbit, and snapped into place with minimal manual handling. Standardization speeds repairs. By deploying a Dyson swarm first, an economy of scale emerges and lessons about thermal management, radiation shielding, and docking interfaces accumulate before the next expansion. A phased approach also helps manage risk. Resource streams from asteroids and minor planets supply the hardware and fuel for in-space manufacturing, minimizing the need to lift everything from a planet and enabling larger radiative cooling surfaces to be added over time. Energy distribution networks must be robust and modular. Contemporary megastructure efforts in space show that large, modular, autonomous systems are feasible on a smaller scale, providing practical analogies for Dyson scale planning. On-orbit servicing and assembly test beds illustrate the viability of long-term operations. Heat rejection, radiation hardening, and reliable power routing remain the dominant technical hurdles, but advances in advanced materials, autonomous robotics, and energy management frameworks push the envelope toward feasible long-lived operation. The payoff is continuity of power for civilization-sized aspirations. Detecting Dyson spheres, signatures, and challenges. A Dyson sphere, as a hypothetical megastructure designed to capture a star's energy, would re-emit the intercepted energy as thermal radiation, shifting most of the star's luminous output into the infrared. That signature is the first clue astronomers chase. In practice, an entire shell or swarm would dampen visible light from the star, while producing a broad, nearly blackbody infrared spectrum that depends on the shell's temperature and geometry. The concept is elegant, but the signatures are subtle. The best starting point is a surplus of infrared emission without a commensurate bright optical counterpart, a mismatch that hints at waste heat rather than a natural luminous process. Astronomers quantify this with spectral energy distributions across wavelengths. Modern all-sky infrared surveys, including data from missions like IRAS and WISE and Spitzer, catalog countless sources with IR excess, and careful filtering aims to separate ordinary dusty stars from truly anomalous objects that could warrant a closer look. Non-dust explanations must be considered too. Partial or irregular structures complicate the picture, because a partial Dyson swarms or a partially cloaked star would still emit infrared radiation but leave detectable traces in the optical or in the timing of light. That makes the search a puzzle rather than a slam dunk. Natural culprits like circumstellar dust shells around aging stars, debris disks around young stars, and even complex interstellar dust can mimic a smooth infrared excess, so follow-up observations are essential. High-resolution imaging and spectroscopy help break the degeneracy. Cross-checks across multiple datasets reduce false positives, using parallax, proper motion, and stellar classification to ensure a candidate truly stands apart from ordinary astrophysical objects. The challenge is non-trivial. Researchers advocate a Dysonian SETI approach, looking for energy use patterns, unusual variability, or abrupt changes in a star's energy budget that natural processes struggle to explain. As data quality improves, the line between imaginative speculation and testable hypothesis narrows. The path to a Dyson-empowered era. Civilizations aiming to harvest star power pursue architectures that scale from modular orbital arrays to a fully integrated megastructure around the star, and in the framework of the Kardashev scale this approach points toward a Type II civilization. A Dyson swarm forms the starting point. In practice, the path begins with abundant photovoltaic modules launched and assembled in orbit, linked into a lattice that can be expanded as demand grows. Robust autonomy makes it feasible. As collectors proliferate, their outputs are routed through distributed energy networks that minimize single points of failure and enable rapid reconfiguration when a sector experiences degradation. From a swarm, civilizations progress to more integrated distribution, converting captured energy into usable power for spacecraft, habitats, and industrial processes across the system. Beaming becomes a primary option. Wireless power transmission through phased array microwave or laser links allows energy to be delivered to distant assets without prohibitively heavy tethering, though it requires precise alignment, atmospheric safety considerations, and disciplined spectrum management. Redundancy matters. Networked control using AI and holographic monitoring helps coordinate thousands of collectors, balancing load, addressing faults, and optimizing beaming schedules to match shifting demand patterns. The practical steps hinge on in-space manufacturing, resource extraction from asteroids and moons, and the creation of resilient energy storage that can tolerate long transit times and solar variability. Robotics perform much of the assembly. Superconducting power lines and cryogenic storage concepts reduce transmission losses and enable compact distribution nodes. But cooling challenges and radiation exposure must be managed with robust shielding and maintenance regimes. Materials recycling closes loops. Standardized interfaces and modular designs allow components from different builders to interoperate, while independent verification ensures safety, reliability, and predictable performance as the system scales. Building toward a Dyson-empowered era also demands governance frameworks, risk management, and ethical norms that keep peaceful access, shared benefits, and planetary protection central. The energy commons approach matters. Civilizations must prepare for stellar activity, debris management, and the socio-economic shifts that accompany a new energy backbone, including fast adaptation to technological breakthroughs and the diversification of energy markets. Experimentation in simulation labs and pilot projects guides the journey. Real-world programs explore incremental steps, from medium-scale orbital farms to multi-system networks, each test refining governance, standards for beaming, and the engineering practices that make a star's energy usable at planetary scales. Today we've traced the arc of the Age of Dyson Spheres. What a Dyson sphere is, why a swarm of energy collectors around a star might come before a single shell, and how harnessing stellar power could redefine technology, economy, and civilization itself. We explored the scale of the opportunity, from vast swarms to more integrated megastructures, and the enormous engineering, resource, and governance hurdles that would come with such projects. We also touched on how such megastructures would change what we can observe in the cosmos, and how we might recognize signs of advanced starfaring life. If you felt that spark of wonder, The sense that the universe could be powered by a civilization thinking at megascale levels. You're not alone. First, I'd love to hear what grabbed you most. The engineering feats, the social transformations, or the signals such civilizations might leave behind. Share your thoughts in the comments. If you enjoyed this journey, consider liking, subscribing, and tapping the notification bell so you don't miss future episodes. And if you're curious about what comes next, we'll be digging into the concrete architectures, Dyson swarm, shell, and other variants, how we might detect them, and what daily life could look like inside a star-powered civilization.